because you were here early. So you were obviously very excited. Now, it's important because, I'm going to move this. It's important because it helps you decide what practices you want, all right? And you'll see pictures of my children. They were a little younger here, but there they are looking at a stormwater control measure. All right. One word I did not share with you, one term I did not share with you yesterday that I should have, is when we put stuff in the ground, like in individual practice, a wetland, a bioretention cell, a permeable pavement, a rainwater harvesting system, which we're going to talk about today, those in America are now called stormwater control measures. All right? I think it's actually a pretty good word, a pretty good term. We used to call them best management practices, and that was not a very good term. You know why? Because a lot of them weren't any good. So how can you call something that's not good best, right? So now we just call them stormwater control measures, and I'm a big fan of that, all right? So the abbreviation for stormwater control measure, anyone want to guess what it is? SCM, all right? So you're going to see it. You're going to see me use the term SCM a lot. It's just another word for green stormwater infrastructure, all right? More or less. So stormwater control measures, or SCMs, are collections of treatment mechanisms, all right? We give them fancy names like constructive stormwater wetland, but the reality is that there are these bundles of treatments that help clean the water or help reduce the volume of runoff. So we're going to go ahead and take a look at a couple of those, a list of those right now, all right? We have, we modify flow. Ideally, and by flow modification, what I mean by that specifically is you take high inflow peaks and you reduce them, all right? So I could put flow mitigation, flow rate mitigation. Infiltration, you know what that is. It's water soaking into the ground. One I don't have listed up there, but evapotranspiration. Hey, look, everybody stand up. Everybody stand up. I'm going to have everybody remember the hydrologic cycle, okay? So I'd like for everyone to put your fingers up into the sky. You are touching the clouds. You're touching the clouds. What is in the cloud? Moisture. All right, I'm tinkling. That's my fingers are raindrops. And so it comes down, whoop, here. Now it's hit the earth. Now where does this water go? 3 places. It can go down. Oh, that's as far as Dr. Hunt goes. That's infiltration, all right? It can go back up, evapotranspiration, and it can run off. So yeah, that's good. We can do runoff like that. I like that. Runoff, you get like, you can do all sorts of things with runoff, all right? But all right, so that's it. 3 things. So thumbs up. What we don't want to do is this. We want to reduce this, even though this is the most fun. We're trying to do as much of this and as much of that. Everyone got it? There's your flow modification. You can sit back down. Now that you feel good, now you're up for the day. Now you feel ready to learn today. Right. You're like, oh my gosh, Dr. Hunt slept last night. I did. I should have gotten here a day earlier, and it just didn't work out. So I ended up landing on Sunday morning. And to teach on Monday after you land in India on Sunday after flying from America, that's a lot. But I slept a little better yesterday, so we're going to see how we go today. I'm feeling pretty good right now. All right. So I just went through the 3 hydro modifications, the hydro treatment. Then there are the pollutant mitigations, so the ones that change the concentrations. Sedimentation, filtration, and gross filtration. Those specifically deal with particle removal, all right? And then chemical absorption, which is what takes dissolved species, most dissolved species of metals and phosphorus out. Chemicals, microbial transformation, which is done by microbes. That helps get rid typically of nitrogen and certain types of pathogens. And then thermal pollution. On how important thermal pollution is here, But if you were to head up towards the Himalayas where the water is cold and doesn't want to get warm, then you can do that. And then desiccation and predation is how you kill pathogens. Whoop, 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 whoop. So let's go ahead and talk about flow modification. When we design practices like ponds and wetlands and then dry basins, we put holes in the outlet structure. You know what those holes are called? Orifice. Orifice. How many of you have heard the term orifice? That's great. Orifice is a really good engineering term, okay? We could just call it a hole, right? But do we want to call it a hole? No. Why don't we want to call it a hole? Doesn't sound fancy, right? They hire engineers to do hard work, right? And as an engineer, you demand to get paid. If you like, I'm going to design a hole for you, people aren't going to pay you anything. But if you say, I'm going to design an orifice, they're like, okay, how many rupees is that going to be? All right. So that's why we use, just remember, we have our own terminology to help us sound smarter. Okay. So there's your orifice. And the orifice is key because it's what changes the flow rate as the water is stored in the basin. There is an issue, though, is that we see really big erosion in non-stabilized streams because of how we design our orifices, all right? Or orify is probably the proper Latin term. All right, I'm going to skip through this just for time's sake. But what I want everyone to, I have a long talk I give on it. I'm going to skip on that. But this is what we start. Well, what we start with is this maroon. Hey, you guys like my hat? I'm going to wear it all day long. At least while we're inside. That was a really nice gift I got. Somebody, who gave me this gift? You're not, she's gone. Where? There you are. I love it. I'm going to love this hat all day long. All right. So we start out with this green, this maroon or brown curve, okay? That's the hydrograph associated with an undeveloped area. And then we develop it. We basically take that field. We were talking about very productive, very fertile soils here in Uttarakhand, okay? And we pave over it. Yesterday, the professor talked about how in Bangalore, which is obviously in the south, they had added 100 square kilometers of city in the last decade. That's a lot. So they're knocking out vegetated areas and they're replacing it with impermeable surfaces. All right. Well, what hydrograph do you get when you knock all the vegetation out and you put up impermeable surfaces? What color? The red one. Right. You guys like music? You know who the Counting Crows are? Anyone know who the Counting Crows are? They paved paradise and put up a parking lot. You guys know that song? Homework. Look that one up. You'll like that. It's basically an environmental song. They paved paradise and they put up a parking lot. All right. Well, that's what's happening in Bangalore. Except they're calling them car parks down there, but you get the idea. All right. So that was the red one. And then we come in like, oh, we got a problem here. Because that red one is what causes stream blowout. Well, it's what causes flooding. The red one's what causes flooding. Like, okay, we need to tamp down the flooding. So they put in that hole, the orifice, to manage the flow rates. And guess what color we get then? What color? It's not red. It's not brown. What's another color up there? Green is what we want to go for, but it actually is orange. They give us the orange one. All right. So what it does is we release the flow rate at a much lower rate what it was initially, but you can see how it extends. It keeps going and going and going and going, right? Well, that might seem okay, except when you hold a flow rate out for a really long period of time, it causes streams to erode, right? And so the only way to mitigate that is actually to start putting more water into the ground and more water up into the atmosphere, okay? So that's why infiltration and evapotranspiration are so important because this orange flow rate, like these are like the Indian flag colors, right? Boom. Green is the best. Orange is actually not great because that orange is what causes that. All right, now let's keep going. So what we want our stormwater control measures to do is to take really a big inflow peaks and reduce them. This is what we've done here. And then we also want to release less water than what we started with. All right. Now, obviously, this graph, this is about a 29 millimeter storm, so it's a medium-sized storm. All right. This graph shows a really high peak flow, and it shows how it was squashed. All right, it was dampened. But what is hard to tell is you don't know how high that peak is. If you integrated under the inflow curve and compared that area to what you integrated under the outflow curve, guess what you'd find? That the inflow area is 20 times more than the outflow area, which is really the inflow volume is 20 times higher than the outflow volume. So what did this practice do? It didn't just reduce the peak, but it released a lot less water, which is very good for stream health. Everyone clear on that? Okay. So and when we can find practices that are good at taking runoff and putting them into the ground and up into the atmosphere, you're going to be like, that's a good stormwater control measure. I'll skip through this one. This is a fancy one. We're not going to talk much about it. It's called regenerative stormwater conveyance, but it doesn't really quite do that. My grad student did that, and that's not quite right, but the water does flow through the media. It just doesn't go up and down. You can vegetate them to get evapotranspiration. These are all things you can do as you build your stormwater control measures. And this particular one did a great job, not only reducing peak flow, but reducing volume. And that's what you want to get when you put stormwater control measures in the ground. Now let's talk about, again, one of the two main ways that you can reduce volume. Infiltration. This is something called an infiltration basin. Infiltration basins work great when you don't have a water table up near the surface. Is that going to be a problem in Rookie? It actually is a problem in Rookie because you guys have a relatively high water table. All right. Now, if it's 1.5 meters or 2 meters away, then you do have some infiltration options. If it's only a meter or certainly a half a meter, then you're not going to infiltrate much water, maybe hardly any water. All right. This particular site, we infiltrated a lot of water. The water table was between 1.5 and 2 meters away from the surface. And you can see we had a 75 millimeter storm. It filled it up. All right. And then the next day, most of that water had soaked back into the soil, which was great. All right. So infiltration is a great way of removing volumes, which helps stream health. Okay. To let that water soak into the ground. Now, the other one we talked about is evaporation and evapotranspiration. There is a practice out there that is particularly good at evapotranspiring. Would someone like to guess what that practice is called? I'll give you a hint. There's a small version of it over my shoulder. All right. I know what would help you guys is if I gave you like buttons that you could press, because then you wouldn't feel awkward about saying something. But you know the answer to this one is, but I'll give you a vote. Is a practice that's really good at evapotranspiration, is that permeable pavement, or is it a green roof? How many of you say permeable pavement is great at evapotranspiration? How many of you say green roofs are great at? Exactly. All right. So green roofs are really good at evapotranspiration. There's also another practice called a blue roof, which in this case looks green. Looks gray. But that's an evaporation. And we'll talk more about blue roofs later. All right. But just know that these practices are designed to evapotranspire. You guys like Johnny Cash? You guys know who Johnny Cash is? The Man in Black? Ring of Fire. You guys know Ring of Fire? I fell into a burning ring of fire. You guys know that song? No? Yeah, I mean, you like, Bill, do you know any Indian songs? Like, no, I don't. So I get it. It's a very popular song from the 1960s in America, Ring of Fire. It's a good one to look up, all right? And that's 2 homework assignments. In fact, I'd rather you learn, I mean, Pay Paradise, but the parking lot's probably better. But Ring of Fire is a great song. Anyway, I wrote a version of that song that talks about evapotranspiration, right? You always know someone loves their craft if they write songs about what they do. I hope all of you feel that way someday in your life and in your career. Write songs and sing songs about your family and write songs about what you do and your job. If you can do both of those things, as long as the song about your family is not about loss and death and sadness, then you know you're doing right. Then you know you're doing right. All right. So here we go. This gray curve, the gray curve, that is the amount of runoff we had from a standard roof. And the green curve and the blue curve, that's the amount of runoff we had from the blue roof and the green roof. What do you see here? About 50% of the water that fell on that roof evapotranspired or evaporated from the blue roof. It's just evaporation. All right? So, infiltration, evapotranspiration. Those are great things to have at your discretion when you're trying to improve pollutant loads. All right. So in North Carolina, in many places, I'm not saying this is correct, but it is how it is. When you're calculating a pollutant load, what you're doing is you're looking at a volume of water and you are multiplying it by the concentration of the pollutant in that volume. So if we want to improve a pollutant load, and so pollutants, while we do worry about concentrations, really what the receiving water wants to know is how many kgs of a pollutant are you dumping into me? All right. If it's like a very small number of kgs with a high concentration, chances are it's okay. I'm not saying you should do that, but chances are it's okay. But if it's a bunch of kgs, then that's a problem, because that's what is going to contaminate, hurt the fish, and all that. And so if you can reduce the volume of water that's being discharged from your practice, then guess what? You're going to reduce your pollutant load. If a lot of water comes in and a little water leaves, even if you don't even change the concentration from here to here, you've reduced your pollutant load. All right. And so in North Carolina, if you reduce the volume of water you discharge, they count that as reducing your pollutant load. All right. Even if you don't change the concentration. So evaporation and infiltration, they both reduce the volume of outflow, and therefore they both help reduce your pollutant load just by doing the volume of outflow improvement. Now, everything else I'm going to talk about is associated with changing your concentration of pollutants. All right. So even if the outflow doesn't change, like we're going to look at constructed wetlands, they don't change outflow a lot. There's a little, but not much. Constructed wetlands, what they're trying to do is lower the concentration of the pollutant from what came in to what left. All right. So there we go. Now let's talk about the pollutant removal mechanisms associated with reducing your concentration. We're going to start with sedimentation. All right, guys, what equation, and you can talk to each other and agree on it before you tell me. What equation do we use to calculate sedimentation rates? Stokes' law. How many of you agree with that? Put your hands up, everybody, because that is the correct answer. Good job. All right. So sedimentation is calculated by Stokes' law. For those of you that want a real quick reminder How many of you are civil or agricultural engineers? How many of you are not? Okay, okay, okay. What's your background? Yes. Hydraulic engineering? Great. How about y'all? Your background? What's that? Environmental engineering. What about y'all? You say geology, geography? Geography. Okay. Anybody else? Mostly engineers here. It's always good to have a geologist and geographer person among us. Anyone else? And you guys have interest in economics? I figure you probably wouldn't be here, but you never know. All right. That means you guys are going to know a lot about what I'm about to share with you. And so it's all going to be a review. The whole idea behind a stormwater control measure is to keep water, for sedimentation purposes, is to keep water in the practice and the particles in the practice so that as the water flows and the particle falls, that it eventually hits the bottom. That's all sedimentation is. All right? And so, as you said before, how quickly a particle falls is determined. We use Stokes' law to determine that. This is for big stuff. You almost don't have to even worry about the big stuff because it all falls out. All right? But Stokes' law, man, that's how we determine if stuff falls out. Now, it's therefore very important. Oh yeah, take a look at this. Take a look at this equation. What is the most important parameter to determine settling velocity? What diameter? And how do you know that? Because there's a 2 next to it, right? 2 squared, right? So therefore, it's the most important parameter. So if you need to know the diameter of, if diameter is the most important parameter, then you need to know the diameter of the particles associated with your runoff. All right. Now, we've done a lot of work in North Carolina looking at typical sediment distributions. All right. And so, for you to have a good feel for how well a practice here will reduce how well sedimentation will work here, you'll need to know, and you probably have it, particle size distributions associated with typical runoff in the rookie area. Okay. In North Carolina, we have a couple of, we actually did a bunch of tests with our transportation ministry. We call it the Department of Transportation. And those are the ranges, our particle size distributions associated with roadway runoff. All right. And if you take a look at it, most roadway runoff, about half of it, is a sand. What's good about sands relative to silts and clays from a sedimentation perspective? What's good about sand? What's that? I think I heard what you said. It settles faster, which means the more sand you got, the more effective sedimentation is going to be. All right? So that's pretty good. About 50% of it was sand, and only a very small fraction, less than 5%, I think, on average, was clay, which is basically about impossible for us to remove. So we could go through and calculate this. I'm not going to do it other than to say that if you're dominated by particles in this range, okay, which fortunately we are not, all right, but if you're dominated by particles in this range and you try to settle them out, in a constructed wetland, I didn't change this. I know I feel badly about it. And you're trying to have it fall 15 centimeters, so forgive me for not converting that. I tried to go through and figure that, but I missed this one. I apologize. It would take that water, the water would need to stay in the wetland for 15 to 16 days. Now tell me a little bit about the rainfall of Rookie. I did a little research on this morning, actually. Is the rainfall in Rookie, does this rainfall pattern good for keeping water in a practice for 15 to 16 days? If you need a storm, the water from a storm and the sediment from the water in a storm to be in a practice for 15 to 16 days, is Rookie's rainfall pattern conducive to that? How does it rain here? A lot. When? What, May, June, July, August? So you get a lot of rain in about 4 months. Does it rain almost every day? Doesn't? Well, that's good. Does it rain every 3 days? A lot of rain every 3 or 4 days? If you continue to get 250 mils of rain, all right, in a month, and it keeps coming, then I don't know how reliable it is going to be that one storm's water is going to hang in your practice for 2 weeks. My hunch is it probably isn't. All right. So sedimentation, what I'm trying to get at, is good. Is not good if you have clays, but it is good if you have sands. All right. So the exact same calculation. This time we're running it for sand particles, and instead of needing weeks, 2 weeks. Thank you for that, by the way. Instead of needing 2 weeks for the particles to fall out, you just need hours. You measure it in hours. So it's in your interest. I mean, it is what it is. You can't change the soil you've got, right? But it's in your interest to have coarser grain particles for sedimentation to work. All right. Thank you so much. Man, you guys are just living. This is great.
This is also filled with tea.
And that's filled with tea?
Yeah.
Man, Rob, you're the man. Thank you. I was telling some of your colleagues that I really love Indian tea. You get great tea in India. I'm going to be honest with you. You don't get great coffee here, but you get great tea. Tea better than I get in the United States. And I love it. When you come to America, where's my Italian? Where's my University? How do you say university? University di Trento. Where's my Trento man? Yeah, you like your coffee there? Are you a cappuccino drinker in Italy? What's that? You like macchiatos? I get that. That's cool. I'm a cappuccino man myself. Over there, I love cappuccinos. But macchiato, you're not going to go wrong with that. Coffee is good in Italy, isn't it? Tea is great in India. You got to love what you got. Okay. So it's better to have sands, but if you don't have sands, what you going to do? What you going to do? Well, you have to move on to another practice, another pollutant removal mechanism, and that one, y'all, would be filtration. Okay. Filtration is the most reliable pollutant removal practice we've got as long as it's working. You might be thinking, what are you talking about? I'll explain that as we go through these slides. Now, in America, the universities all have mascots. All right. Does Rookie have a mascot? I haven't seen it, so I'm going to guess it doesn't. I have a feeling it's more of an American thing. So my university, the mascot is the wolf pack. All right. The most popular mascot in America, you might be interested in, is something that doesn't live in America, but it lives in India. You know what the most popular mascot in America is? The tiger. Lots of tigers. The Princeton Tigers, the Auburn Tigers, the Clemson Tigers. A lot of tigers. There are 2 wolf packs. All right. Well, the University of Maryland, their mascot, you ready for this? Is a turtle. That doesn't scare me. I don't scare you. The idea of a mascot should be to scare you, because they're your soccer team, your basketball team. They're the wolf pack, but then Maryland has a turtle. Like we're the turtles. They're called the terrapins specifically. If you see a turtle in the bottom of the slide, guess where I got that slide from? My buddy at the University of Maryland, Dr. Davis. Dr. Davis and I wrote a book. Because any of you are interested, it's not cheap, guys. I wish I could, it's not cheap. But if you're going to be in the stormwater world, you might want the book. We have most everything is in SI, so you'll like that part. But we do have some things in imperial units as well. But we go through all this. A lot of basically everything I'm telling you is in the book. It's in that book. But it's not cheap. It's like 120 bucks. I'm done. I'm not average. I mean, if you want the book, I think it's a good book. Dr. Davis, the guy from the land of the turtle, is a very good writer. And he wrote the chapter on filtration. All right. So that's engineer for filtration. That's a picture of filtration. And this is the equation associated with filtration theory. And take a look that there's a fair amount associated with it. Now, I could have y'all, I'll go back and show you this equation. All right. I could have y'all calculate filtration out. All right. We could do that. But you know what? We don't have to. Do you know why? Because basically, everything that comes in to a stormwater control measure that employs filtration gets removed. That's just how it is. Hello, sir. It's good to see you again. Hey, Professor Oja, I went to go see your tree again today. It's still there. I noticed, though, that the sign with your name is hidden compared to all the other trees. So it's like you're operating in the shadows. I like it. I like that style. All right. If anyone does not know, he has a tree. He planted a tree on this campus. If I could get a tree, that would be like one of the greatest honors. I hope you feel that way. I'm sure you do. It's like a big honor. Anyway, near the Thompson building, there's a tree that he's planted. How tall will that tree get someday? No, I've been in. Okay, so here we go. Going back to this. We could have you calculate. I could give you the parameters, but you know what the calculation would say? It would say 100% removal. All right? Oh my gosh, we're multiple. You guys expect me to eat a lot of cookies today. That's great. I love cookies. All right, so filtration works great, and I'm going to show you an example. So we've got two different types of permeable pavement. Those are the PICPs. Then we've got this practice that has step pools that water filters in through the media. Then we've got a Silva cell, which is a proprietary system. In America, in Australia as well, proprietary products are very popular. What do I mean by proprietary products? What does that sound like it means? I'm going to break you guys down before I'm done. What does it sound like? It's a proprietary product. What does proprietary mean? What's that? That's good. That's exactly right. It means that someone has created a product that they're trying to sell you. All right? That's how big an industry stormwater is in America and Australia, that all these, and in Europe too, but Australia especially, in the United States, they have lots of people that make things that you buy off, we say off the shelf, and put in your pond, put in your wetland. You basically just put it in on its own, all right? So Silva Cell is a proprietary thing that is basically a filtration-based practice that's under a sidewalk, under a parking lot. But it's basically they put a media in and the water soaks through the media, perks through the media. And then BRC is bioretention. Now look at that. Look at the data on me, over my shoulder, or well over my shoulder. Look at the inlet concentrations. Look at the outlet concentrations. And all these things are based on filtration. What do these data tell you very clearly? Does filtration work or not work? It works. It works. You might be wondering, why are those concentrations zero? Because even the media or the gravel has small particles in it that are like present, that get washed out when it rains. All right? But anytime, like our limit, the limit, if we see any of those outlet concentrations under 20, we're like, well, that's pretty good. All right? all but one of them was under 10. These are really good numbers. And to compare those to the numbers that came in, all right? So filtration practices work great if we're trying to remove particles, okay? They work great until they don't. Now, what do you think that means? What if you have really high sedimentation loads coming in? See that picture on the top? That was a high sedimentation load coming in. How well, for filtration practices to work, what does the water have to be able to do through the media? Percolate, right? Talking about coffee earlier. Has to percolate. Is water going to perk through that? Nope. So infiltration-based practices, and infiltration works great until it does such a good job I meant filtration rather, until it does such a good job of filtering that it binds itself and clogs. All right. And so there's a happy median. If a practice clogs because it's done such a good job of filtering, is it done for good? Meaning, will it never work again? What do you guys think? The answer is it won't work again until you maintain it. This is going to be one of the most important things I share with everybody in this room today, is that there is no such thing as a maintenance-free stormwater control measure. I need everyone to be 100% clear on that. There's no such thing as a maintenance-free SCM. As a result of that, in the United States, one of the classes I teach frequently is on inspection and maintenance of stormwater control measures. We have trained, I don't know, 6,000 people have come through that class. I'd usually teach 4 to 5 of them a year. We've trained, and we've done it since 2006 or 2007. One of those 2 years. So we have over 6,000 people we've trained. Because if you don't have an industry, a maintenance industry, coupled with your stormwater installation, then you know what? It's wasted money. You guys have seen something get put in the ground and it doesn't work very well because it got neglected. Like everyone's seen that. Imagine getting a car and not taking care of it. What eventually will happen? It'll break. I mean, the worst case, you don't even put gas in it, right? It'll stop. There's a lot of EVs on this campus. I appreciate that. It will stop. Well, the same is true with an SCM. There's no such thing as a maintenance-free SCM. We're hardly going to talk about that over the course of this week. Filtration. Gauge filtration basically means if it's a big particle and you can grab it like this, it's going to get caught. Is everyone on board with that? Unless it's really lightweight and it blows through. But basically, all practices are able to do a pretty good job of capturing large stuff. But do we have large stuff here in Rookie? We do in America. I walk around, I see a lot of like trash. We've got trash. Stormwater control measures do great at capturing trash, but that also has got to be maintained. All right. Just remember, if it does a good job of employing these removal mechanisms, then it's going to have to also be maintained. flows downhill. If trash is carried in that water, guess where it's flowing? Downhill. All right. And if all that water is flowing to a stormwater control measure, then all the stuff in it is flowing to that same stormwater control measure. All right. So I can't stress enough how important maintenance is going to be as these things go underground. Because I took this in the United States. You understand, across the globe, we have issues with extra trash that will get into our stormwater control measures. I can't imagine it will be any different here. All right. Now I want to move on from the physical realm to the chemical realm. And I'll be honest. Here too. All right. And so therefore, when we're designing a stormwater control measure, a filtration-based one, in addition to sand, which is almost always going to be part of a filtration-based practice, what other material do we need to put in there if we're trying to get rid of things like oils and greases? What do you think? What does an oil or grease want to bind to? I'll give you a hint. It's represented by OM up there. It's organic matter. All right? So you got to have organic matter in your stormwater control measure, media, if you want to get rid of things like oils and greases and other organic pollutants. All right? So crafting the media that the water is going to percolate through is actually a very important job for stormwater designers. All right? Now, based stormwater control measure, as the runoff comes in, it's trapping the clays, the silts, the sands. But you know what else is trapping? Organic particles. Kind of cool, right? And guess what then attaches themselves to the organic particles that the stormwater control measure just trapped? Oils and greases. So it's literally removing one pollutant. And as it removes one pollutant, you get the add-on benefit of another pollutant getting taken out. That's pretty cool, right? Now, some of you might be thinking, how does, once you remove the PAH, does it just hang there for eternity? Well, I've got good news for you for that one. And the answer is no. Because there are microbes in our media. It's kind of exciting, right? There's a lot of life going on inside your SCM. All right. They're like bad boy Pac-Men. These are like hungry Pac-Men. All right. When you see that, that's a microorganism, according to my friend from the University of Maryland. That's a microorganism. And so the PAHs, they get captured at the top of your media, all right? They're sitting in there, they're on the organic matter. As long as it's moist, control measure, you think it's moist in stormwater control measure? Is there moisture in a stormwater control? Yes, there is. That's why it's there. Stormwater is there for a reason, right? Is there oxygen up near the surface? Yep. If it's working right, there's oxygen up near the surface. And are there micronutrients? You're just going to just accept that there are micronutrients there. So you know what happens? These microbes that want to devour PAHs, for example, they have the perfect stormwater control measures, the perfect environment for them to basically have nuclear reactors on campus. All right. They don't produce power to the campus, but they're there because we train nuclear engineers on campus. What he did is he took 2 batches of bioretention media, filter media, all right? And he took 1 batch and he stuck it into the nuclear reactor. And guess what he did? They zapped it. They zapped that media. So what would all that radiation do to anything that's in the media? Anything that's alive in the media. What would that radiation do to it? You think it's good for it? You're right. It kills it. Kills it. Okay. So then what he did is he took motor oil and he dumped it, he poured it onto both media. All right. He poured it onto the media that had been zapped by the reactor, and he poured it onto the media that had not been touched. All right. That just like onto the media that had gotten zapped. What do you see? What do you see? What you see is that one had a bunch of microbes in it that devoured the motor oil. The other one didn't have any microbes left because it got zapped and everything was still there. Do you see the power of the microbe? Let me ask you guys this. When we design our stormwater control measures, do we think, oh, we better put some microbes in there? Nope, we don't. You know why we don't? Because they're there. Isn't that cool? They're there. They're just waiting to be energized. And that all the oil comes in, and boom, they're excited and they get to go eat. By the way, what they're turning this stuff into is water, oxygen. It's not bad. We're good. Inorganic absorption is a little bit different. And what it essentially means is for most pollutants, you want to make and 14. All right, 12, 13, 14. And that's when they introduce those age children to dance. They have dances, all right? And it's rock and roll music normally. So you know what the boys do at the dance? No, you know what the girls do when they go to the dance? You're going to be shocked by this. They dance. The girls are out there dancing. Do you know what the boys do? You guys want to guess what the boys do? I'm going to show you what the boys do. They stand up against the wall and they watch the girl dance. Okay? That's what they do. They watch the girl dance. And then all of a sudden, the slow dance song comes on. The slow dance song. You know what that song's for? To encourage the boys to dance with the girls. All right? So then this boy, they have to summon the courage. And they go out and they ask such and such girl, would you like to dance with me during this slow song? Guys, that's essentially what happens in soil particles. All right? So the hydroxyl, OH, it is dancing with iron. And they're dancing like this. Iron or aluminum, all right, I'll dance with you. I don't really want to, but I'll do it. But you know what they're doing the whole time? She's looking for the man the boy she really wants to dance with. You know who she really wants to dance with? Ortho P. She wants to dance with the dissolved phosphorus in the worst way. And guess who shows up into the room? Dissolved phosphorus. So guess what happens at the end of the dance to the hydroxyl ion? When that dance is over, she says, see you later. And she says, come dance with me, dissolve P. You know what dissolve P does? Says, yeah, I'll dance with you. Do you think they dance like this? That's correct. They actually embrace and hold each other. And that is how stormwater control measures remove dissolved is actually very pretty. I tell my sons, learn cursive. You know why? Because girls like it. It's true. I write little notes to people I love in cursive, and they love it. All right. There you go. That's how inorganic absorption works. By the way, pH matters. So the more acidic it is, the harder it is, even though aluminum or iron loves dancing with zinc, the more acidic it gets, the less it wants to hold on to zinc. All right. So you want more neutral, a nice neutral situation, so that the dance goes on forever. All right. Now let's move on to biological transformation. It's particularly important for nitrogen removal. All right. So there's three principal types of nitrogen that's coming into our stormwater control measures. Organic nitrogen and ammonia got the certain microbes convert the organic nitrogen into ammonia, and then that ammonia in that same organic oxygenated environment breaks down. My other set of microbes break it down into nitrite, nitrate being the stable state. And then you need to have the nitrate enter an anoxic environment where there's no oxygen, where denitrification to N2 gas takes place. All right? So what does that mean from a stormwater control measure design standpoint? In your bioretention cell or in your filtration-based practice, you've got to make sure you have zones that have oxygen, and then you've got to make sure you've got zones that don't have any oxygen if you want to get rid of nitrogen or break pollutant forms of nitrogen down to N2 gas. N2 gas, obviously, it's what, 78% of the atmosphere? It's a lot of the atmosphere, so that's no problem. Now, that can be a challenge. So therefore, practices that are consistently aerobic, so that basically everything is oxygen, they will actually end up discharging or leaching nitrate out. All right? They will leach nitrate out. And we see that happen a lot. And nitrate is a problem. It's hard to remove. And once it's getting in the water column, it can cause algal blooms and stuff like that. All right? And so it's important when we design stormwater control measures to intentionally put in our design to intentionally create zones that will likely become anoxic. All right, remember this. We're going to talk about bioretention on Friday. All right, so, but as a designer, you have to be thinking about how am I going to get my aerobic water going through an aerobic zone to hit an anoxic zone. That's an important part of what we do. All right, so just remember that. And I'm going to give you an example where we studied this in a bioretention cell. Okay, for the nitrogen cycle to go through, all right, for the microbes to be happy, we have to have a carbon source. Is this my time to leave? Do I need to stop? What's that? We'll take a break for 10 minutes. You guys ready for a 10-minute break? Yeah? Okay, I was on a roll. I'm good with that. It is 11 o'clock. I will look at my watch from now on, so I'm getting fired up. This is a good spot. We'll come back and we'll resume discussing a nitrate. We have about 10, 12 more minutes to go on this talk. So we'll take a T8. You got to hold the water long enough that you get that the microbial breakdown has enough time. That's what I used to look like. That is a long time. In fact, how many of you are like 24 right now? 25. Yeah, that's what I looked like when I was your age. Woo! Boy, things have changed. That's a plant. I know it doesn't look like one. Trust me, it's a plant. This is a wetland. It rains. It saturates the soil. Everything in and around in the media is saturated. It's anaerobic. It's anoxic. But you see those roots? You can tell those are the roots. That's the gray things. They have oxygen around them. Like the roots will have oxygen like in and around them. So guess what you got? You've got anoxic zones intermingled. Really, you got aerobic zones intermingled with anoxic zones. You know what that means? That means you've got the perfect environment for denitrification to occur. So constructed stormwater wetlands are particularly good. All right? They're particularly good at getting rid of nitrogen. Bacteria. Bacteria are hitchhikers. All right? So you got your bacteria, they're riding along on your sediment. Well, how do you get rid of sediment? What are the two ways you get rid of sediment? We talked about them. What are the two mechanisms? I heard sedimentation. What's the other one? Filtration. You got it. And so if bacteria is hitchhiking with sediment and you filter the sediment out, then guess what? You're also filtering out the bacteria. All right. But remember, bacteria are alive. Okay. They're alive. And because they're alive, that means they can grow. It also means that they can be food to something else. And that's essentially what we see here. It's hard to tell, but there's an amoeba coming in to eat a bacterium. Protozoa are particularly good eaters of it. All right. So remember that column, that the nuclear reactor up in Maryland? Again, he took one media, he zapped it, he killed all the predators. All right. The other media he didn't do anything with. One, he zapped it and then added protozoa. The zapped column without predators, and this is logarithmic, that's the bacteria population. It grew because they're alive. But even with the zap column he added protozoa to, look, those numbers plummeted because the bacteria were being preyed upon. All right. And the BSM is a fancy mix that he was testing. All right. Obviously, it worked even better. The point being is that in your media, you've got the bugs, you've got the microbes that are eventually going to wipe out the bacteria you trap. Now, how cool is that? All right. Heat exchange, pretty simple. Hot water, cool media. Is the water hot that runs off asphalt? Well, how hot does it get here? I know the answer is. I had a close idea. How hot does it get in Rookie in June? Hot. 40, 45. That's hot. How hot's the asphalt? Hot. Super hot. Probably, I don't know, 80. It's hot. What happens when it rains in the afternoon? Yeah, I see you guys doing it. You know the answer. The heat that's in the asphalt transfers to the water, and you got really hot water. Guess who hates hot water? Most fish. They don't like hot baths. All right. And so if your practice can cool the water down before it gets discharged, then it's going to be very good for aquatic life. So bioretention, for example, will hold water in and get it cool. That helps a lot. Infiltration helps a lot. Permeable pavement. If you go down a third of a meter and the temperature is much cooler down there, that hot water will actually stay and mix with the cooler gravel. And when it discharges, it's much lower temperature. So all these base stormwater control measures are able to cool the water down, which is particularly good. All right, I'll skip through that. I'll try to skip through that. Oops, okay. So I'm going to close with this. Stormwater control measures, again, are collections of pollutant removal mechanisms. You see them behind me right here. And so really, when we are trying to choose the best stormwater control measure, or in some cases, if we're trying to fine-tune the design of a specific type of stormwater control measure, we want to think about what removal mechanisms that are being employed in that stormwater control measure and make sure that we match the pollutant removal mechanisms to the pollutants we're trying to treat. Okay? And it just so happens that there's only a few stormwater control measures that have essentially all of those pollutant removal mechanisms. Okay? Most of them only have a bundle of a subset of them. Do we have any questions before we now take our break? All right, you guys happy I slept better last night? I hope you are. I feel good. I know I feel good. How long should our break be today, this morning? 10 minutes.